Welcome to this video on limits and discontinuity. This is one for part B. We're going to look at specifically evaluating limits algebraically in this one. In the last video, we talked about how to find limits kind of graphically, and then to determine is a function continuous or not. So here we go. Let's look at examples 15 and 16. And it says that x values where a function is continuous, limits can be found by direct substitution. So here we're looking at these examples, and all they want us to do is evaluate the limit. So in order to determine this limit, and they're kind of implying that these functions are continuous. And this is polynomial. And polynomials are continuous. Polynomials, I don't know, I don't need an apostrophe there. Polynomials are continuous, okay, for all real values. So all you have to do, right, to find the limit is they want to know, okay, what's the limit at 3? So I plug in 3, and I'm done. That's it. This would be your answer, okay? The AP exam grants the point if you leave it in numerical form. Okay, so I mean, this is 29, right? You can calculate this, but if you get that wrong, then you would lose the point. Whereas if you just left it in numerical form, you get the point. Okay, number 16. What's the limit as x approaches 1 for the rational function x squared plus x over x plus 1? And again, like I said, this is a rational function. This is continuous except for, right, at your value x plus 1. Okay, so, and actually what you're going to get here, I factor out an x plus 1. These cancel, and so you're going to have a discontinuity, a hole at -1. X plus 1 equals 0. So x is equal to -1. Okay, and all this, this is all just kind of backstory. You don't really need this to do this problem. They just want you to directly substitute. So I'm being extra. But here you have a hole. Okay, so they want you to evaluate what's the limit at x equals 1. So our function is continuous at 1. We can just go ahead and evaluate. So I plug in 1. So 1 squared plus 1 divided by 1 plus 1. That's 2 over 2, which is 1. Okay, so here's your limit. All right, so that's evaluating limits algebraically just via direct substitution. So if you ever have a problem that says what's the limit of f of x and f of x is continuous, all you have to do is just plug in that value. It makes it kind of nice. Second topic of this lesson is piecewise functions. So we're going to calculate the limit of piecewise functions. The problem with piecewise functions is they have a break, right? They're in pieces. So in order for a limit to exist, in order for the limit of a function f of x as x approaches c to exist, the left and the right limits have to be equal, right? As x approaches, the value from the right has to be equal to the value from the left. Okay, so that's algebraically kind of your definition of a limit, right? The conditions. So what we're going to do is I'm going to determine, okay, the limit of f of x as x approaches 1 from the left. What is it? So notice for a piecewise function, right, here is our domain. So the domain, if x is less than or equal to 1, so if I'm approaching 1 from the left, that's going to be this function here. Okay, so I'm going to plug in 1 there. So 4 minus 1, this gives me 3. Okay, and now I'll calculate the limit as x approaches 1 from the right. Okay, so from the right, that's going to be my x value is greater than 1. So I'll plug in 1, which we get 4 times 1, which is 4, minus 1, so that would also be 3. So hey, what do you know? They are equivalent, so our answer is 3. Okay, in 18, we're asked the same type of thing, okay? So I'm going to go ahead and calculate the limit of g of x. That's an m, I promise. As x approaches 1 from the left, so again, that's this function here, right? Because if I'm approaching 1 from the left, I'm less than 1. And so I plug in 1, and we get 3 times 1, which is 3, minus 1 cubed, which is 1. This is equal to 2. And for the right side, the limit g of x as x approaches 1 from the right. Okay, and this gives us 2 times 1, which is 2. Take away 1, that is 1. So notice how these are not equal. So does not exist. The limit does not exist. D and E. Okay, 19. For the same function g of x, what's the limit at negative 1? Well, this is pretty easy, right? I mean, negative 1, right? That's going to be to the left. To the left. So we're just going to strictly use this function here. Okay, so I'm going to plug it in. So we get 3 times negative 1 minus negative 1 cubed. Okay, and that would be suffice. This would be your answer. That would be the limit. Okay, but if we want to calculate it, that's negative 3 minus negative 1. Okay, which turns into a plus 1. So negative 3 plus 1, which is negative 2. All right, the last topic that we're going to address here is the greatest integer function, or also known as a step function or a floor function. And it is written here, so f of x equals x, and it kind of has these brackets, and I don't know why this got cut off, but it should look like this, okay? And they want us to calculate this. Find the following limits. So what is the limit of the greatest integer function as x approaches 1/2? So visually, and you can see this here, visually, if I go to 1/2, notice 1/2 is probably about here. From the left and the right, I do have a value, and that value is 0. Now, what the greatest floor function, or the greatest integer function, does is it takes the value less than or equal to x. Okay, so if I'm at 1/2, what's the biggest integer less than or equal to 1/2? And that's 0, right? 0 is the biggest number. Okay, but if I get to 1, right, the biggest value less than or equal to 1, that value is 1. So everything from 1 to 1.1 to 1.2, 1.3, all those values are going to be 1. So if we look at 1, right, which is here, okay, as I approach from the left, my limit's 1. As I approach from the right, my limit is 0. Okay, so notice how those do not equal the same value, right? The limits are not the same value, so this does not exist. All right, so in this video, we talked about calculating limits algebraically, okay? And if you have a continuous function, you can evaluate via direct substitution. And then we talked about limits of piecewise functions, okay? And setting those equal to each other.